about. So today we'll be talking about quantization. And the motivation here is that, as we all know, these models, these language models are very large. They have a lot of parameters. And so this makes it difficult to run inference on a variety of devices. Let's say I want to run inference of a language model, have it generate text for me on my laptop. Or let's say that I only have one GPU. Let's say I'm using like Google Colab and I just have a T4 GPU, but I want to use, say, an 8 billion parameter model or one that's even larger. It also makes it difficult to fine-tune on a variety of devices. Let's say again that I only have one GPU and I want to fine-tune, say, a 72 billion parameter model. Am I completely doomed, or is there actually something that I can do? So hopefully by the end of this lecture, you'll have some insight into some of the answers for these challenges. And then also, even if you're considering pre-training or just training a model from scratch, then the previous lecture was really the main underlying idea was how do we use compute most efficiently? And so there's a question of like, as we'll see, do you even need to use kind of full precision to pre-train a model, or can you kind of save compute or use it more efficiently by quantizing it? Still an open question, but again, hopefully you'll get some insight into it after seeing the techniques today. And as I mentioned, what we'll talk about today is very practical and you'll see it in a lot of places. So let me just start with a concrete example. And here, this is just introducing the problem. So let's say we want to use this model Qwen3 8B, really recent model. And so we go to Hugging Face and we start taking a look at it. Well, first of all, what are the implications of 8B? So we have 8 billion parameters. And let's actually just look on the website. And if we take a look at how the parameters are stored, then here we see that they use something called BF16. So I'll introduce what BF16 is in the lecture. But you could see here that this means it's using 16 bits for each parameter. And so that means, 16 bits will be 2 bytes. So it's 8 bits per byte. And so if you multiply those two, you get 16 billion. And so that is the definition of gigabyte. So now you have 16 gigabytes is required to kind of store this model. And in fact, here you could see the exact number of bytes and you see 16 at the end. So just to double check the argument there. Okay, and then this is just a rough approximation, but hopefully in the last lecture, you got some appreciation for the memory that's involved in using a model. So we don't have to only consider the memory required for storing the weights, but you also have to factor in things like activations as you're performing a forward pass through the model. So just for this really simple argument, let's just say you need about 1.5 times the gigabytes needed for the model weights to actually run inference. Again, it's just a kind of, I just made that up, but it's going to be some multiplier of your model weights. So let's say it's 24 gigabytes of memory. Now, this is a MacBook Air, and so this one, I think it's a cheaper one. And so it has 16 gigabytes of memory. And so what are the implications here? Well, essentially, in order to run inference with this model, it's going to actually have to write to disk and kind of swap out. It's not going to be able to hold everything in memory. And so that's really going to slow things down. Let's say that you're using Google Colab. So these T4 GPUs that you get for free are 16 gigabytes. And so again, we're going to run into an issue here. Basically, we're either going to run out of memory, or the most recent version of Hugging Face, I think, will again offload things. So you won't be using the GPU memory, it'll be swapping things in and out, and it'll just be really slow. Okay, so this is an issue, but it turns out that there's ways around it, which is what we'll talk about today. So what we'll talk about is quantization. And so here the key idea is to represent each model weight. And if you want the activations, which are just numbers, using a smaller number of bits. So instead of 16, for instance, let's say that we use just 4 bits. Well, now we can have a smaller version of the model. So here's an actual example. Here they have a version of Qwen3 8B that is 4 bits, and you could see it's just 6 gigabytes. Okay, so now there's some hope of actually running this, say, on my laptop and having it run a bit faster, or fitting it into that GPU that we get for free on Google Colab. And so today we'll talk about 3 different topics. First, we'll go over, might be a review, but I think some of it should be new, just how you represent numbers on a computer. And so we'll look at indeed, we'll get a kind of really good understanding of what we mean when we say like B float 16 or float 32 or int 32, things like that. Then we'll look at 2 different categories of methods, and we'll mostly focus on the first category, which is, let's say that you want to run inference with a model. So you want to generate text with a trained model. How can you use quantization to help with that? Then in the third part, we'll talk about the intersection of quantization and training. So either training a model so that you can use it as a quantized model during inference, or using quantization to help make training more efficient. Okay, so you'll see what I mean by both of those things when we get to it. Okay, so first representing numbers. So you might remember from, if you took this like computer architecture class or something like that, going over this stuff. But it's good to recap it and kind of start from first principles, and we could build up an understanding of what's involved in quantization. So really just starting at the top, we represent data in the computer using sequences of bits. And so a bit is either 0 or 1. And then we refer to 8 bits as a byte. So here's 2 example bytes. Now, the way that you'll represent numbers or store them depends on the type of the number. So 3 different types you might consider are, let's say you only have integers that are non-negative, right? So 0, 1, 2, 3, those will be called unsigned integers. Or you could have negative numbers, so that would be integers. Or you could have real valued numbers. So things like 12.34, things with decimals, they could be positive or negative. So starting with the unsigned integers, here let's look at a byte. And so here, each position will represent a power of 2. So this first position will represent 2 to the 0. The second will represent 2 to the 1, and so on up to 2 to the 7th in this case. And then the value of the number that this represents will be the sum of the powers corresponding to the positions with a 1. Okay, so this is basically saying ignore this position, and take the sum of these, sum of the ones with 1. And so our number will be 1 times 2 to the 6th plus 1 times 2 to the 4th plus 1 times 2 squared plus 1 times 2 to the 1st. You can add those up and you get 86. And so that would be the integer represented by this byte. Okay, and so then here we have 8 bits or 1 byte. And so you would refer to that as U8 or 8-bit unsigned integer. And then you could think about what is the range of this data type. Well, it's 2 to the 8th and then subtract 1. And so you have 255. You could also have 16 bits, so 2 bytes integers. That would be U16. Here you have a larger range now, 65,000. And then if you go up to 32 bits, you have, right, 2 to the 32 minus 1, which is much bigger. So basically, as you use more memory or more storage, you can get wider range of values. Then if you want to also have negatives, then you have to have the notion of assigned integer. So here we'll use the leftmost bit to represent the sign. And so now we just have these 7 bits for kind of representing the value. And then the common algorithm or representation that's used is called 2's complement. And basically it boils down to doing the following. So let's say I have this number and I want to represent its negative. Then what you do is you flip all of the bits and then add 1. It's kind of what the algorithm boils down to. And so here this would be the negative of the number that was previously shown. Okay, and so then here now you could have an int8 data type, which means assigned integer represented with 8 bits. And so now again, we're using this first bit for the sign. So now we have from between negative 128 to 127. And so for the positives, you kind of use up one of the values to represent 0. Okay, so you can see that this is relatively kind of small window of numbers. Surprisingly, we're going to actually use this to store the model weights. And then you can go up to int 16 or int 32 if, again, you want a kind of wider range of numbers. Okay, so then we could move to real values. So it turns out that you can't actually represent every possible real value. You have to kind of choose a subset. And so what are called floating point numbers and a particular representation of floating point numbers will give you the ability to represent some amount of real valued numbers. So the way these work is a bit different than the integers. So this is again going over the kind of standard way of representing floating point. So here you have these 3 different types of values. You have a sign, you have an exponent, and you have what's called the significand. And so the value is going to be what's down here. And you could think of it as being like, okay, let's say you have a decimal, then the significand is kind of helping represent what is to the right-hand side of the decimal. And then the exponent is helping kind of scale the value. And then the sign is, of course, whether it's positive or negative. Now, what's done in in practice is to use what's called a bias. So we'll see in the example in a bit. You can use this bias so that you can represent this exponent as an unsigned integer, and it turns out to be good for hardware and for it's kind of what's done in the standard. And so what you could think of this as is a kind of analogy to scientific notation, except here the tricky part is that we're actually using base 2. So for instance, here if you have 1.101 times 2 to the third, then it doesn't actually mean 0.101. It means 1 plus 0.5, and then a 0. So this is 2 to the minus 1. And then this position is 2 to the minus 2, and it's zeroed out. Then this is 2 to the minus 3. And so you see 2 to the minus 3 appear here. So it's a bit weird if it's the first time you're seeing this, but it's essentially this kind of scientific notation, but in base 2. So again, here instead of having 10 to the whatever power, like in scientific notation, we have 2 to that power. So let's walk through an example just to make sure we understand what's going on here. So let's actually think about what number is represented by this and kind of step through it. So first of all, we see that the sign is positive. If it's a 1, it would be negative. And then we could consider the exponent. So here we have this unsigned integer. So this is 128 and this is 1. So we have 129. And then as I mentioned, you typically have this bias. So for this version of floating point, this is floating point 32. There's 32 bits. They use a bias of 127. And so actually this exponent represents the number 2. Then the significand, so all of these are zeros, so we can just look at this starting point. And the 1 here is kind of implicit. So it's basically saying that, okay, this represents 1.0110000. And then again, we're using this base 2. So this is basically saying, okay, 1 plus 0 times 2 to the minus 1 plus 1 times 2 to the minus 2 plus 1 times 2 to the minus 3, and then the rest are zeros. So that equals 1 plus 0.25 plus 1 over 4, and then 1 over 8. Okay, so this part, the significand ends up representing 1.375. Okay, so now we can combine all of them, and you have 1.375 times 2 to the 2. So this floating point number represents 5.5. Okay, so it's a bit complicated, but it turns out that this is how you represent the kind of decimal values in the computer. And so we'll see variations on this, so it's good to kind of step through the details.
Is the 127 like the bias, is that just like a fixed number that's kind of predetermined by the computer's own architecture, or like almost always be 27?
Yeah, so I think here it's because we have this unsigned integer. And so you can represent you could represent a negative exponent by having say like 0 minus 127. So then you could have minus 127. And then you could represent minus 126 by setting 1. So you basically have the range of an unsigned integer, but then you're just storing, sorry, you have a range of a signed integer, but you're storing the unsigned integer. Yeah. So it's determined by how many bits you have in the exponent. Yeah.
Sort of split determined, like do we sometimes see
Mhm.
larger amount allocated to exponent versus significand, or is that like
Yeah, that's a great question. So I think it's the next slide. Yeah. So I'll talk through this a bit. So here we have float 32, which is what we just went through. And this is usually referred to as full precision. You'll see these terms, you'll come across them, so it's good to know what that refers to. And that just refers to what is shown here. Then you could have float 16, which is called half precision. And so now you could see that both the exponent and the significand were reduced. So then there's actually one more that's commonly used, and it's called B float 16. Does anyone know what the B stands for? It's kind of trivia. Yeah, brain. So this was invented by Google Brain. So it was like invented in a machine learning context. And so we could think about like what are the pros and cons of adjusting the exponent and the significand. You could see that this B float 16 is basically keeping the exponent the same as float 32. And then you just have a budget of 16, so they reduce the significand. Whereas float 16 kind of reduced both. Anyone have any thoughts on um, the kind of trade-offs? Yeah, exactly. So the exponent in some sense controls the range, right? The kind of, the range or the scale. And then the significand really helps with more finer grained precision. And so I think what was observed in training is that in training the neural networks, or it might have not been language models, just neural networks, large values were being encountered, and then training would basically crash. And so here you could basically retain the same range as full precision, and then maybe that leads to fewer crashes in training. Of course, you do give up some ability to represent, yeah, the more kind of fine-grained differences. Okay, so then this B float was invented, and as we saw in the case of Quen 3, they're actually representing their model in B float 16 instead of float 16. Okay, so does that help answer the question? Okay. So, okay, so we went over this. So yeah, again, we can look at the Quen 3 example, and you could see here that here's the exact weights. And if you haven't seen this before, you can take a look at this. Wait, how did I do that? There we go. Okay, so any model that's on Hugging Face, you can kind of look at the weights. And so here you could see that everything's stored in this BF16. Okay, and then of course the trade-off with float 32. Float 32 looks kind of strictly better, right? But the trade-off is going to be memory. Basically, the size of the model will double if you go to float 32 instead of the B float 16 or float 16. Okay, so that's the basics of representing numbers, so both integers and the floating point numbers. Anyone have any other questions on that before we start to talk about the actual methods and language model inference, things like that? Mhm.
So they all have the same kind of precision rows.
Mhm.
Do we generally see kind of that happening where like we all use the same precision for the entire thing, or do we see like kind of like alternating?
Yeah, that's a really great question. So yeah, you'll typically actually see this mixed precision. So some operations will be more like more important to kind of represent in a higher precision, or they'll be particularly kind of cheap layers to just represent in a higher precision. And so especially when we actually start talking about the quantization, it's typical for not 100% of the model to be quantized. You'll pick the kind of most expensive layers, so like the feed-forward layers, things like that, to quantize, and then you'll have other layers in a higher precision. So like the output layer might be in a higher precision. Yeah. Mhm.
Much more like a bigger data set in training, but rather than correlation wise, it always the inference typically takes one number.
Yeah, so here we're just splitting it into two different parts for almost like practical reasons. So let's say that, these big companies train the model, and then a variety of people with a variety of devices want to run the model on their kind of budget. It's like such a common use case that you could consider like trying to do really efficient inference. But then training is actually typically more expensive because you have the gradients involved, all the stuff we talked about last lecture. One difference is that during pre-training, you might pre-train with a small context length and then kind of post-train with a really long context length. And then in inference, you also use a really long context length. So that could lead to some differences between like pre-training and inference. But yeah, it's just broken into two different categories because kind of doing efficient inference is useful on its own. And then you could consider different methods for training. Mhm.
For the B flow representation, did they have to come up with specialized hardware to do like multiplication and things like that?
Yeah, so the different representations will be, yeah, you want them to be supported by different hardware. And so I don't know the history of that one in particular, But yeah, like the GPU will only have certain operations, um, like certain floating point operations, certain integer operations. And so you're kind of in the short term tied to whatever the device supports. And then if you do develop a number representation that's like better and people start using it, then maybe the hardware will build it in. Yeah.
What sorts of devices support the this the support GPU?
Yeah, I mean, I think it should, yeah. I'll actually talk through a couple more examples on this theme of like the hardware support too. Okay, so yeah, maybe I didn't say what quantization was yet, which is why the slide is here. So quantization is just in general the process of mapping input values from some large set, could be like continuous values, to output values in a smaller set. And I guess the name quantize usually means that the smaller set is also kind of discrete. And so an example in our context is we want to map some higher precision format like float 32 to some lower precision format like say int 8. And so an example quantization method is just kind of normal rounding. So you could take a real number x and then just round it to the nearest integer value. And that is a kind of legitimate quantization method. Now, the question is, how much error do you incur with a given quantization method? And so error would be the difference between the input value and its quantized value. So here, for instance, if we take 1.4 and use the technique of rounding, then the error would be what, 0.4. Similarly, here we would incur an error. And you can also see this issue that comes up. Since we're going from a larger set to a smaller set, you can run into these kind of collisions. Like two different numbers are being mapped to the same quantized value. And so the question is, can we do a bit better than just rounding? And so let me introduce two different methods, but first let's like specialize it a bit to language models. So if you look at the large transformer language models, then this is something I was mentioning before, that just the feed forward and attention projection layers and the kind of involved matrix multiplications make up about 95% of the model's parameters and between 65 and 85% of the computation that's involved. Right, so there's all these other layers like activations, like layer norm, things like that. If you look at these, which are kind of repeated multiple times, they're going to make up a large percentage of the parameters and computation. So the goal is going to be to quantize these parameters to fewer bits. So for instance, b float 16 or float 32 to int 8. So here I'm going to introduce some of the, I guess, early methods for really large language models. And I think at the time, one reason that this int 8 was very popular was again because it was supported by hardware. You could do like int 8 multiplication, int 8 addition, things like that. Since then, there's been specific data types developed, like specific 4-bit representations of floating point. So I'll mention those later. But for now, we're going to focus on going to these quantizing into integer values. Okay, then if you can do that, then you can use this low bit matrix multiplication, which you again assume is kind of supported by the hardware, and then you can save a lot of memory. Okay, so let me introduce two different methods. So this one is called abs max or absolute maximum. And so here we start with some input matrix. Let's say it's in float 16. It's actually not too important what you start off in. And you have kind of sequence length times the hidden dimension. Our goal is to produce a tensor of the same size, so sequence length and hidden dimension, except the numbers will be different. Now we'll have int 8 kind of values in the tensor. Okay, so this absolute maximum is like it sounds. So basically, you look at the matrix and you get the maximum value after taking the maximum magnitude value. And then you divide every value in the matrix by it. So now you have things that are between -1 and 1. Then you scale it to be in this 8-bit range by multiplying it by 127. Okay, so kind of simple method. And so here in the code examples, we have some examples of actually doing this. So let me see, should have it running here. So yeah, so we could start off with this array and then just implement what was there. And then to dequantize, you would basically kind of do the reverse. So you would divide by this scale, the scale being 127 divided by the max. So here we have our original array, and now we have our quantized array, which is integers. And then after we dequantize, here's what we get. And so you can see we incur some error. A little bit here, the 4 is kind of perfect, and that's our error. Here is just, if you want to play around with different examples, here's just showing how you could start off with something that's a decimal. And I don't know, at least the first time I saw this, it's kind of surprising that you can actually, map it to integers and kind of recover the decimal value. Of course, not perfectly, you do incur some error. So then we could consider what is involved in doing a matrix multiplication. Again, right, matrix multiplication is kind of this fundamental thing we want to be able to do. So here's one way to do it. So here you have an input matrix and a weight matrix. You want to multiply them together. Well, what you can have here is the kind of two scales that you get during quantization. And then here you have some integer matrix. We'll come back to this in a bit, but you could see here it is basically quantizing this matrix X and quantizing the matrix W. That's what the notation represents. And then, yeah, for each one, you're going to have this scale parameter that you can divide by to kind of dequantize. So this is representing both, the quantization and dequantization. Now what happens is, let's say you multiply two 8-bit numbers together. Let's say you have, 127 by 127 times 127. Well, then that's going to exceed the capacity of 8-bit. And so what's typically done is you have this buffer that is in a higher precision, say like 32-bit integers, and you would implement the matrix multiplication where it's kind of adding to this buffer so it doesn't exceed the value. Okay, so then on the actual hardware, it's going to be up to the kind of hardware provider to do this efficiently as possible. Now, there's one other thing you could do, and I'm going over this kind of quickly, but you could think about matrices, and you could think about the way that you do matrix multiplication. And it basically comes down to a bunch of, row times column, and then you take the dot product and add together. So what you can do is you can actually separately quantize each row of the input matrix and each column of the output matrix. And then kind of for each dot product, you'll have one of these scale multiplications to dequantize. And so you can do this kind of more fine-grained, it's called vector-wise quantization. And that'll turn out to reduce the error. So this is also in the code example, and again, it's kind of just cool to look through. So here we have just a random matrix that we're starting with, and you have the weight matrix and some input matrix. After you run the quantization, now everything is integers. So this will be what happens, in the actual neural network. This is just a little toy example. Then you can perform the matrix multiplication. You could see that it exceeds the range of int 8, so you need to have the output be stored in higher. And then here is kind of rescaling it or kind of dequantizing it. Okay, and then if you do the actual or if you do matrix multiplication without the quantization, here's what you get. And so then you can look at the errors. So that's really what's going to be happening in these techniques. Instead of these toy examples, we're going to have actual weights in the neural network, and we're going to have actual, input features. But yeah, kind of cool, kind of crazy that you can just convert things to integers. Uh, a bit unintuitive in some sense. Okay, so then here's just one more method. And the reason I'm telling you about this is if you do go do more reading about quantization, then you'll see some of these ideas come up like offsets and scaling. And so it's kind of worth going through these and yeah, knowing about these techniques. So here's another one called 0 point. And the basic idea is to kind of implement this concept here. So here we have the minimum and maximum for some float values. And we want to basically map this shouldn't be minus, should be plus. We want to map the maximum representation, the maximum value to the maximum int 8 value. And we want to map the minimum value to the minimum int 8 value. Okay, and so the reason is that now we can kind of take advantage of all of the numbers that we have available to us in int 8. So what it boils down to is something that looks like this. So you take your floating point number, you multiply it by a scale, and you round, and then you add this kind of offset, and that'll be sufficient to do this. So there's a blog post that goes through the steps of all this. I should add it as a supplementary reading. If you're curious, you can walk through the derivation. But it comes down to the scale is basically the total number of values you have in int 8, and then you subtract the range. So this is sometimes called dynamic range, because here you have this max and min. And then the offset turns out to be this. Again, if you kind of step through the argument, it's nothing crazy. You could see that this scale is appearing here and the minimum, and then you're kind of shifting by this minimum value, and there's a rounding operation as well. So I won't go through the full justification for it. Then if you want to dequantize, you basically do the kind of reverse operation. So you have int 8, you would subtract the offset, and then divide by the scale. Okay, and so the key difference here is that it's kind of designed so that, again, you're taking advantage of the full range of int 8. And so in particular, this is really good for really asymmetric data. So if you consider the activations after a ReLU operation, then they're going to be non-negative. And so if you use this abs max method, it's going to just divide by the maximum, and basically nothing is going to be negative. So you're only going to use kind of half of the available numbers that you have in int 8. Okay, so that's an advantage of using this kind of 0 point method. And And so this is just showing the same thing is implemented again in the notebook. Let me see if on this example, does it use the same? So here we got 9.3 times 10 to the minus 5. This is just one example. This is slightly lower, so 6.9 times 10 to the minus 5 error. But the point is that, or I mean, one interesting thing to see here is again, here you have minus 128 show up and 127, like I was showing you on the slide. Okay, so as we observed, even in these really simple examples, so this was like a vector with 4 elements, and they weren't kind of high precision decimals, we do incur errors. And so these are going to accumulate when we have like really large weight matrices, like the total error. And so you are losing some information when you're doing the quantization. Now, the issue is if you kind of think about these for a while, then there's actually a big issue in both of these quantization methods that I talked about. And the issue is what happens if we have a really outlier value? Well, both of these methods, they in some sense depend on the minimum and the maximum. You know, we saw like minimum and maximum appearing in both formulas. And so it turns out that they're going to be very sensitive, or they're going to have kind of poor performance if we have outlier values. So here's an example, and again, you could run this on your own if you want. Here's an example where we have this array, and it basically differs by this last element. So in this case, the last element is 100, and in this case, it is kind of similar to the other elements. Now we can look at the quantized array, and you could see that, you know, everything's either being mapped to 0 or 1. This outlier kind of, you know, screwed things up. And so, yeah, quantitatively, you're going to have a high mean squared error. Same thing is happening here with the 0 point. You can see everything is being kind of packed into these low values here, all due to this one outlier. Without the outlier, it's different. You get a lower error, and the quantizations look a lot different. Okay, so you're probably wondering, like, why am I going into so much detail on this? Like, why is this interesting? Well, you might find it interesting just in its own right, but it turns out that this outlier phenomenon actually appears in large language models and really leads to huge degradation in performance of the quantization. And so here's a really kind of influential work, and it's by Tim Detmers, who's now a professor here at CMU, and it's called llama.cpp. So what they basically observed is that these transformer language models have certain features that are outliers. So if you look at the columns of the activations, then they noticed that consistently the networks would have, yeah, these columns, which were just like much bigger than the other ones. And the interesting thing is like these outliers were appearing mostly in large language models. So models of over 6.7 billion parameters or over, these would occur kind of more frequently. And in particular, some outlier there would be at least one outlier in 100% of the layers in the network as you kind of pass activations through on kind of, you know, reasonable real data. And so the hypothesis then is that quantization kind of wasn't working well for the really large models. And so the hypothesis is that there's this huge performance degradation due to these outlier features. And so here you could again kind of convince yourself of this by looking at a really simple example. So here what we've done is we've taken this matrix multiplication example, and we've just set one column to, we've scaled it up by 100. And so now you could see here you have this what we were calling outlier feature. And then when we quantize and do the matrix multiplication, now you're getting a much bigger mean squared error. Maybe I should have shown the previous one, but the error was kind of orders of magnitude smaller without the outlier. And hopefully it shouldn't be too surprising based on what we were just discussing. So what they basically did is say like, okay, if these outliers are occurring, then maybe we can break down the matrix multiplications in the network into high precision and low precision. We can perform the outlier computations that involve outliers in a high precision and perform the other computations in low precision and then kind of merge the results. And so the interesting thing is that although these outliers appeared in every layer, they would only be some really small percentage of the features. And so only like 0.1% of all features in the network are outliers. So this is kind of good because then if we break apart the computations, we're still saving a lot of memory or a lot of compute because this is only a kind of, I guess the features themselves are outliers in some sense. So here's the picture. So again, here you have X and you have the weight matrix. And you could consider again how matrix multiplication is performed. And you can see that, okay, for this outlier feature, it corresponds to, performing some multiplication with these rows of, or it'll be multiplied by these rows of the weight matrix. So you could basically split up the computation. So down here, you could do, say, 16-bit multiplication. Up here, you could do, say, 8-bit multiplication after quantizing and dequantizing. And then you can kind of merge the results, so add them together. So that's really the key idea behind this method, LLM int 8. And they have this really cool plot if you haven't seen it before. So, so here on the x-axis, we have the parameters in the language model. And then here we have accuracy on a bunch of benchmarks like average together. And you could see here that if you use quantization in orange to 8 bits, it's actually doing kind of well for these smaller models. And then right when you hit 6 billion parameters, it's not working too well. Okay, so then they found that these outliers were really occurring in the large models. And then after you use their method, which kind of splits apart the computations, now you can do pretty much just as well as the 16-bit model. So it's really cool. And I think on Tim's blog, he goes into some possible reasons for these outliers. I think one reason is that the network can use it to kind of erase things. So if you have a really large value, then you can like cancel out things after taking a softmax. I'm kind of hand waving. You'd have to look at the details to convince yourself of that. But yeah, so it could be that, these outliers are effective for like implementing different things and the model kind of learns to use them somehow. And then here's just showing, well, one part is to show that the stuff I introduced is kind of showing up here, and then also to show their improvements. So you could see the abs max and 0 point, and then this is perplexity, so lower is better. And you can see, yeah, their LM intake method is basically recovering the perplexity of the 32-bit model, which is pretty impressive. So I think that's my last slide on this int 8. I want to show this library. So if you want to use this, then it's also implemented. You can see it's a pretty popular library. It's called Bits and Bytes. And it's also integrated in with Hugging Face. So here you could see that you have this LM int 8 or 8-bit quantization. And so then you can use this to kind of run inference with a model on a variety of devices. So instead of doing a code example with this, I'm going to go over another library that's really popular. But any questions on this before we kind of go to the next part?
Yeah. So it seems from the quantization methods we have covered until now is that you scale and shift mainly, which is like you're assuming that you would want to quantize uniformly across like the number range. Are there methods where they explore like non-uniform quantization so that you have more precision at like a smaller bound, but not as precise than like very small numbers or very large numbers?
Probably. So there's other methods that we're not going over that will actually do a kind of learned strategy. So they'll say if you consider quantizing this one column, then you'll incur some error. So then set the rest of the weights to values that like minimize the error. And so it might end up looking a little bit different than the techniques you use here. Yeah. Any other questions? Okay. So yeah, I was considering whether to put that in the lecture. The method I just mentioned is called GPTQ, or a follow-up is called AWQ, and you'll see that used a lot as well. So yeah, you might take a look at that after. But here I want to introduce this method, and it turns out to use kind of more naive quantization, but this library is really popular, and I'm sure you'll run into it. So it's kind of three different things. GGML, GGUF, and llama.cpp. So GGML refers to this library for tensor operations, and it kind of has its own quantization methods. And so an example is they have this naming scheme, and they have like 20 different types of quantization. So we can just walk through an example here, and then I'll show you that this is really used in practice, which is why I'm going through the details. So an example method is called Q4_K. And so what this does is it basically groups the weights together into blocks. So you break apart the weights into blocks, and then you're going to quantize each block individually. So here, for instance, this particular method will use, it'll have these super blocks. Each one will have 8 blocks, and then each block has 32 weights. And then this will use 4-bit precision. Okay, so some of the variation methods will be kind of how they split things apart. Then you'll compute, it'll again be based on this kind of scaling and offsets. And then you can store those numbers as using some format. Here they choose 6-bit. And then this Q4KS basically means use this strategy for all tensors in the network. Then you'll also see this like Q4KM, and that means you use this Q6K, this is a typo. You use 6-bit for half of certain layers in the network, and you use this Q4 for the rest. And again, I'm not sure how they decided this. I looked at this pull request, and they like don't have a paper about the quantization method, and they say we don't want to write a paper, we just want to build a tool. So, but yeah, these are the methods. And so there's some mixture of basically deciding this block size, deciding how many bits you're using, and then they decide like, do you have everything in low bit or some other layers in slightly higher bits? And then the idea is the library will support multiple backends. So you can run it on Metal, which is like the Mac specific runtime. You could run it on an ARM CPU or on CUDA. Then two more things. So then this gguf is made by the same group, and it's just a file format for storing architectures that kind of use the things up here. And then finally, there's this really popular library called llama.cpp, again by the same group. And it'll be a kind of library for language model inference that uses these things. So it'll use models that are stored in this format, and it'll use these quantization techniques. So this is just, so it's open source, so you can go look at the code if you want, and they basically implemented everything, and it's supposed to be efficient. And then we can look at an actual example. So as I mentioned, this kind of took off in popularity. And so you'll see these types of methods being used a lot. So here you can see Qwen, like the official Qwen team, released these gguf versions of Qwen 3. And here you can see what I was just explaining. So there's a Q4 KM that'll be 5 GB, or you could go up to Q5 KM or Q6 or Q8. So that's what I was just explaining before. And again, as you go up in higher bit, typically it'll have less error, less performance degradation, but it'll be a larger model. Then what you could do is you could go to this llama.cpp library and install it yourself, and then you could run these versions of models that people have uploaded. So then here in the second part, there's this notebook that just has 2 lines. So first of all, it's installing llama.cpp. And then here it's actually taking the model that I just showed you, Qwen 3, the quantized version. And here it's just running on my MacBook Air. So you could see here maybe a few things. So you could see that it detected that it's Apple M4. So it's going to use the relevant backend code for that. And yeah, then here's just some other stuff. And then the interesting thing is that this just came out a week ago, but you could basically have your own version of ChatGPT just running running here. So this is on localhost, and it's basically hosting this Qwen 3 model. And then I have this kind of ChatGPT interface. So tell me about NLP at CMU. Now you do get an appreciation for how fast ChatGPT is. So this will be one of these reasoning models. So here it's kind of reasoning through the query, but this is literally running like on the laptop. Okay, so I need to explain what advanced NLP like at CMU. Let me start by so thanks for a while. Hopefully eventually we'll get to the output. Anyone have any questions about this while it's generating? So anyways, there's a few of these libraries now, and I'll probably go into them more in the inference lecture. llama.cpp, there's other ones that are maybe by startups, ollama or LM Studio. And so now with these quantized models, you can kind of feasibly run, reasonably sized models, and you could see that. I mean, the speed is not too terrible. Just on your laptop if you want. So when I tried this before, it wasn't very good. It hallucinates a lot, or it just doesn't know that advanced NLP is a course. Yeah, it just talks about advanced NLP education. Okay. So so that's that. And then again, you'll probably see these models everywhere. So now you have some understanding of them. And you can also quantize your own models if you want. So then here is what I was talking about before. So I've been talking a lot about the integers, but especially since this quantization started taking off and LLMs started taking off, now even like new formats are being designed. So here's one that NVIDIA created, NVIDIA FP4. And it's basically their own 4-bit representation of floating point numbers. And you could see that here they released it with this GPU architecture. So like the old architecture wouldn't support this format. And as I was telling you about before, if you want to read about the details, you see some of these ideas that we talked about come up. So they have like blocks, they have scaling, things like that. So hopefully you should have enough understanding if you want to learn a bit more. Okay, so the trade-offs. So quantization, of course, reduces the memory requirements. And I guess I didn't go into too much detail, but in practice, you may or probably will see some performance degradation based on the method. So if you look at different papers, like the int8 quantization paper, they do argue that by taking care of the outliers, you don't see any performance degradation. I'm not really sure, like, since then, whether there's different findings, but as we'll see on the subsequent slides, that you are able to improve over these methods with some additional training, which suggests that there is a degradation. Then, as I mentioned, the llama.cpp, excuse me, uses a more, if you want, naive quantization. And there you can look at like their benchmarks and usually see this trade-off with amount of quantization and performance in terms of like perplexity, things like that. Okay, so in the last part, I wanted to briefly talk about quantization and training. So here, there's this idea of quantization-aware training, or QAT. Everything is an acronym. And so the motivation here is, let's say you've pre-trained a model. Now you want to somehow fine-tune it so that it's kind of ready to be deployed as a quantized model. So the basic idea is to insert these quantization operations into the computational graph and then fine-tune the model. And then so basically it's learning, like the quantization is occurring, and so it has to learn how to, get good loss with this quantization operation kind of inside of the network. So concretely, what you could do is something like this. So you could look at a given model layer, let's say, some feed-forward layer or something like that. And then you could basically simulate the process of quantizing and dequantizing. So here you have the input, which will be, or the current, activations in the network, which will be X float. Then you can, simulate the quantization and then dequantize. And I'm saying simulate because here it's never converting this into an actual, integer or something like that. Everything is still in float 32. You're just doing the actual operations like rounding and scaling, and then the reverse operation. Okay, so now the model has to learn to kind of not have its performance degrade after, now that it has the quantized values. Okay, so this screenshot is actually from this PyTorch blog, and then here's some experiments they ran. And it's a bit small, but this is what I was telling you about before. So here you have no quantization in blue, and you have the quantization-aware training in orange. And then at inference time, this is going to be using an actual lower precision, whereas the blue bar is using a higher precision. Now, PTQ refers to the set of methods that just quantize a model after it's been trained. So post-training quantization. So that'll include things like, what llama.cpp is doing or anything in that family of methods. And you could see by doing this additional training, they're doing a bit better than the PTQ. Maybe actually there's an exception right here. Here's another example from NVIDIA. And you could see, again, this difference between the training and the non-training based methods. The dark green will be the training based one. This one is actually, they go one step further and they do this quantization aware distillation. So again, I'm not going to go into too much details, but basically they have the quantization aware. So they basically do distillation where one version of the model is the original model and the other one is like the quantization aware model. And then you can minimize this like distillation loss between the two and basically train the model to be quantization aware. Okay, so sometimes you do see these kind of large differences, and I think this is a kind of active area that's still being investigated. But here's a kind of really recent example. I think this model was released, I don't know, last week or 2 weeks ago, something like that. And here you could see that they did this quantization aware training. And so the model is kind of trained to specifically operate in int4. So then you could do kind of efficient inference, you could have really long context lengths, things like that. Okay, so I think that was all I wanted to say here. And then this is the last thing to mention. Again, I'm just kind of pointing you to these things. I wasn't sure how much time there would be, so I'm not going into too much detail. This is a kind of different motivation. This is saying we want to fine tune a really large model, say on a small GPU. How do we do that? Well, you could try to take advantage of quantization. So here is this method called QLoRA. Again, the first author was Tim. And here what they're doing is you represent the model that you want to fine tune in 4 bits. Then you do the actual updates in a higher precision. So then you do the LoRa thing where you have the LoRa layers, and those can actually be in a higher precision. So you save a lot of memory by representing the model this way, but then you can still have high precision updates. Then additionally, they do this kind of paging. So if you run out of GPU memory, you can kind of split things apart and offload things to CPU. So this will slow down the fine tuning. But then they have these kind of nice results that were like kind of shocking at the time where they fine tune, I forgot exactly what it was, like 175 billion parameter model on 1 GPU or 3 GPUs, something like that. Okay, so again, if you look through different libraries, or this will be in that bits and bytes, you might see this QLoRA technique, and it's still really helpful if you want to kind of fine tune a large model with a small number of GPU compute. Okay, so to recap, we went over 3 different things. So we went over how to represent numbers on a computer, talked about floating point and integers. We talked about quantizing for the purpose of doing inference efficiently. So 2 different methods, this issue of outliers, and then some different approaches. So this LLM int8 and the llama.cpp approach. Finally, we kind of quickly went over some topics related to training. So training a model so that it's kind of ready to be used, quantized at inference time, and using quantization to make fine-tuning more kind of feasible or efficient. And so it turns out that there's a lot of other methods. There's just a lot of research in this area, but hopefully you should have enough kind of knowledge to go like read about these things if you're interested. Like I mentioned, another method that I've seen pop up a lot is this kind of GPTQ or AWQ method. So you might see these things come up and you can kind of look into what's supported or what are the trade-offs with them. And then I showed you at least one library that you could use if you want to like run the quantized models on your laptop, something like that. Okay, so that's it for today's lecture, and there's time for questions if anyone had any.